All right, everybody, welcome back. We are going to pick up where we left off in Chapter 8, talking about eliminations. So, last time, we talked about the basically the nuts and bolts of what goes into an elimination, or specifically what we call a dehydrohalogenation reaction, right? Where basically you take an alkyl halide, you lose a halide part of it, you lose an H on an adjacent carbon, called a beta hydrogen. That's where we get the term dehydrohalogenation, right? And we saw a few different little nuances of that and how we can actually end up with different products. Now we want to start talking about the mechanisms. And what you're going to see here is kind of analogous to what we did last chapter. Remember when we did SN2 and SN1 mechanisms? We're going to see again, very similar comparisons between a couple of different types of elimination mechanisms that we see with alkyl halides. All right. So the first one I want to talk about is going to be E2. And you can probably figure out what that stands for, right? E is for elimination. 2 is going to be second order, just like we saw with SN2 reactions. All right. So just like with the substitutions, we can kind of make a little checklist of, number one, some features, and then number two, some preferred components that are used. All right. So if we're looking at E2 reactions, first thing we can look at is the mechanism itself. Is this going to be a concerted mechanism, or is this going to be a stepwise mechanism? Well, the E2 mechanism in a lot of ways is very, very similar to the SN2 mechanism. One of the similarities it has, that it is a concerted mechanism. In other words, it is one step. All right. Here's how it works. Basically, you have an alkyl halide, and we'll use a simple one like this, right? And what you do is you're going to add a base. And for right now, I'm going to just leave it as generic base, but we'll talk in a little bit about the types of bases that can be used. All right, what the base does is it's going to target a beta hydrogen. And I've drawn one of the beta hydrogens sitting there just so we can show the mechanism. This base is going to grab that beta hydrogen. I did a really bad job of circling the H, but there it is. And when it takes the hydrogen, it's going to leave a pair of electrons behind. These electrons can fall into a double bond between the beta and the alpha carbons, and in turn, it kicks off your X minus, in this case, bromide. Right? So that allows you to form a double bond. You also end up with a protonated base and Br minus as byproducts. Okay? All of this happens at one time. You form the double bond, and you pluck the proton, and the leaving group leaves all at the same time. All right? So, concerted mechanism. Whoops, I did not mean to erase that. I want to circle it. Let's look at the 2. Well, what did the 2 stand for in SN2? Well, it stood for second order, right? We saw that when we wrote the rate equation for an SN2 reaction that both of the reactants were involved in the rate determining step, so it led us to write a rate equation that would give us a second order give us a second order reaction. Getting a little tongue tied here. All right. Well, let's take a look here. Let me erase some of this. Let's write a rate equation for this. All right. You're going to approach it the same way as you did for substitutions. You always start off with rate equals K, and then we're going to look at the specific reactants that were involved in the rate determining step. Now, since this is just a one-step reaction, it's easy. We look at everything that was involved in that one step, right? Well, our alkyl halide certainly was a reactant that was involved, so it goes there. And our base. And just like we've seen in the past, with the components that we're using, they're not going to have anything different than an exponent of 1 here. So we can say 1 plus 1 equals 2. This is a second order reaction. All right? Easy peasy. All right, and I want to do this again, except I'm going to give you a specific example of a base, because next what we want to do is we want to look at writing the transition states. All right, so I want to have actual atoms there to work with instead of just a generic thing that says base. So I'm just actually just going to put the same alkyl halide up. And let's put a more exact system in here. One of the bases that can be used for these types of reactions could be OH minus, right? Hydroxide, you guys know that's a base, right? And, just like we've seen before, hydroxide, I'm writing OH minus just as shorthand here, but we would get it from like sodium hydroxide or potassium hydroxide. We would also want to have a solvent here. I'm going to put some acetone in. Now, one thing you may be asking yourselves at this point is, this looks kind of familiar. This kind of looks like something we did in Chapter 7. And you would be absolutely correct, it does. We'll get to that a little bit later. But suffice it to say, in this context, we're going to look at this as an elimination, as an E2 reaction. Right? So if OH minus acts as a base, it can grab that proton. These electrons can move down, form a double bond, and that leaves, boom, 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 and we get our products. In this case, our protonated base is water and Br minus. All right. Well, let's see if we can draw the transition state. All right. Well, since it's a one-step reaction, that means we're only going to have one transition state. And you approach it the same exact way that we did in the last chapter, right? You want to draw all the bonds that are breaking and forming as little dotted lines, right? So there's a lot of stuff going on here. We're in the middle of breaking that carbon-hydrogen bond. At the same time, we're also in the middle of forming this bond from oxygen to hydrogen. The Br is in the middle of leaving, and we're in the middle of forming this double bond right here. So there's there's a little diagram that shows all the bond formations and breakages. We do need to put in partial charges. Again, you approach this the same way. All right. Let's see. That OH, for example, right? That O started off negative, but if you look at the products, the O is neutral, so that oxygen, whoa, there we go. Stylus is a little unpredictable sometimes. That oxygen is going to have a partial negative. Br originally was neutral, in the end is negative, so it's also going to have a partial negative. And if you look through, those are going to be the only items that are going to have partial charges. So that would be your transition state for this reaction. Very good. Any questions? No? No? Everybody understands it? Perfect. Ha ha ha. When I'm teaching to an iPad, I have to also talk to the voices in my head, so if I have some weird conversations, just let me know. I really miss being in front of a class, so you got to cut me some slack here. All right. Okay, so those are a couple of the distinct features of E2 reactions. I want to talk about the requirements now. What do we actually need? Okay? Well, just like with substitution reactions, we saw that we used a certain type of alkyl halides that were favored. We used certain types of nucleophiles that were favored. We used certain types of solvents. That's what we're going to see here as well. All right? So if we're looking at the preferences, I guess is a good term, we're going to go in a similar order of importance. Again, the first thing that's most important is the type of alkyl halide. All right. If you remember when we did SN2 reactions, we saw that methyl and primary alkyl halides were by far and away the best to use for SN2 reactions, followed by secondaries, and then we saw that tertiaries basically didn't react at all, right? Well, and I also said there's some similarities between SN2 and E2. Here's where you see a difference, though. We actually see an opposite trend. Tertiary alkyl halides actually work best, followed by secondary, followed by primary. You can do it with all of them, right? Primaries, even though they're the slowest ones, they're still capable of undergoing E2 reactions. Of course, methyl halides are not an option here because methyl halides have no beta carbons, so they can't have beta hydrogen. So we're just dealing with these three. But it's definitely something that's a little bit different than what we saw with SN2 reactions. Here's a big question. Why? Well, if you think about it, with SN2 reactions, why was the order the way it was? I think if you go back and look, you'll see that the order was because of steric hindrance, right? We said it was just simply too crowded once you had like a tertiary alkyl halide for that incoming nucleophile to actually get to the carbon and make a bond, right? So less crowded alkyl halides worked better. However, in this case, the base, right, that we're using, not a nucleophile, but a base, it doesn't have to get all the way into close proximity to a carbon. It just has to pluck a hydrogen from the periphery, and it doesn't have to get as close to do that. So steric crowding, steric hindrance, is not an issue. It's basically a non-factor, right? What actually determines the preferences here is going to be the stability of alkene products. Yeah. Here's an example. Let's say we had something like this. Oh, what do I want to do? Let's see. I thought I had an example written in my notes, but I don't, so I'm having to go off the top of my head. And that's a little scary. Let's try this one. Yeah, this is a good example. All right. So let's take a look at this. Let's say we went through an E2 reaction with this. Okay? Now, one thing you'll notice is that there's actually a couple of different beta hydrogens, so we can actually get a couple of different products here. We could get this, but we could also get this. Ask yourself, according to Zayatsev's rule, which one of these is the major product in this reaction? It's going to be this one, because this one is tri-substituted. We said that the more substituted an alkene group is, the more stable it is, and the easier it is to form, right? So, this is a tertiary alkyl halide. This allows us to produce a very substituted product. Very stable, very easy to form. All right, keep that in mind. I'm about to erase. Now, let's say instead I had used something like this. Let's say I use this primary alkyl halide. Now, in this case, well, number one, we only have one type of beta hydrogen here. We can only make this product. What type of product is this one? What type of alkene is this? It's a di-substituted alkene, right? Not as stable. Tertiary alkyl halides tend to make the most substituted alkene products. Primary alkyl halides tend to make the least substituted, right? That's why you see this particular order of reactivity, okay? Production of more stable substituted alkene products. And that's going to be important to note. All right. So that's one thing we look at, and that's the most important. The next is the type of base. And this is analogous to what we looked at with nucleophiles, right? We saw that SN2 reactions worked best with strong nucleophiles. E2 reactions work best with strong bases. And your book should have some common strong bases that are used, right? You know, OH minus is commonly used. OR groups are really commonly used. One particular OR group that's used a lot is this guy, which is called tert butoxide. And it's really nice because it's a really, really strong base, and as we learned last chapter, it's pretty much a non-nucleophile. All right. So strong bases, and then solvents. This is going to be very similar to what we saw with SN2 reactions. Just like with those, we use polar aprotic solvents. Polar aprotic solvents. So acetone, DMSO, THF, those type of things. All right. I want to run you through another reaction here that's got a full setup here. It's pretty much paint by numbers and applying the steps to figure out the products, but still there's a bit more to it to doing this with eliminations than it is with substitutions. You see, there's a lot more possibilities. And you knew this from the lesson we did the other day when we talked about different types of beta hydrogens and different types of stereochemistry as well, cis, trans, and EZ. All right, I want to show you just how complex this can get. All right, so let's say we had this set up. All right, I'm going to make tert butoxide my base. I'll use some DMSO as a solvent. All right, so this is something I do really commonly, is I might give you a question like this, and I'll say, draw all possible organic products of this reaction and draw a representative mechanism. And the reason I say a representative mechanism is because if you drew every single mechanism of every single thing happening here, that would be quite messy and I think a little bit redundant to gauging your understanding. Here's what I mean. All right, you know this is going to be an E2 reaction because of the setup, and you know part of the E2 reaction, the base is going to pluck a beta hydrogen, right? Now, if you look at this, how many different types of beta hydrogen do you have? You actually have 3, right? You have beta hydrogens here, here, and here, right? So what we're going to do, just for the mechanism part, we're going to show what happens at one of these, all right? So I'm going to just use a beta hydrogen at this carbon. All right, the mechanism proceeds exactly the way you would think it would. You're going to grab that hydrogen. These electrons will swoop into a double bond, and the leaving group leaves, right? And so you know you're going to make a double bond between those 2 carbons. So there's a product, right? But however, you know that's not necessarily the only product that you get, right? You know you had other beta hydrogens, right? So what you would need to do then is be sure to go back and account for the other possibilities. I wouldn't ask you to draw the mechanisms for these necessarily, but it's good to know, and just in case you need to do it like on some scratch paper, right? You should be able to recognize that you would also get a double bond between those 2 carbons and a double bond between these 2. Whoops. Yeah. So 3 different constitutional isomers because of 3 different types of beta hydrogens that were present. Cool, huh? At least I think so. However, guess what? We're not done yet. Why? Guess what we haven't accounted for? We haven't accounted for stereochemistry. Remember, I said previously, it is very common to, whenever you make, for example, a trans product, to also get the cis product with it. Same thing for E and Z. And I'll talk about this a little bit more in a few minutes. All right? But let's take a look at our products and see what we have. All right? If we take a look at this one over here, all right, what do we have? Well, we have a tri-substituted alkene, right? The highest priority group on the left-hand carbon of the double bond is going to be your ethyl group. The highest priority group in your other carbon in the double bond is also an ethyl group. Are those ethyl groups on the same side or the opposite side of that double bond? They're on opposite, right? So this means you have an E isomer. It is also possible to have the Z isomer as well, where they're on the same side. So you got to account for that as well. That is a legitimate product. Now, let's take a look at this one. Same thing, right? As drawn, we should be able to recognize that we have an E isomer. So we're also going to be able to draw the Z isomer. Then if we look at this one, you'll notice that we don't have anything. Switching groups would not give us a different product here, so we're just kind of stuck with that. So overall, we have 5 different products. Holy crap. Yeah, you see, these can definitely get a bit more intensive than the substitutions. So be sure to do a lot of practice problems in working these out. Again, I'm not going to ask you to do all the mechanisms for these, but I will oftentimes ask you to draw a representative one. All right. Okay. Deep breaths. Let's talk a little bit more about these stereochemical situations. Let's talk about stereochemistry of E2. And we can get a little bit of insight on how it's possible to get more than one, like cis or trans or E or Z. Okay, so if we're looking at the stereochemistry of E2 reactions, when you're having an E2 reaction, you're taking away a beta hydrogen and you're taking away a halide at the same time, right? There's a couple of different sort of arrangements that you can have of these two guys. Remember, you have constant rotation around carbon-carbon single bonds. Sort of like just like helicopter blades turning around a rotor. Sometimes you'll have a situation where the H and the X are lined up right next to each other, sort of like this. Right? When they're on the same side like this is called a syn paraplanar arrangement. And it's transitional, right? All of this is transitional. You're constantly spinning, spinning, spinning. At another point of the spin, those two items might be arranged differently to each other. They might be sort of on completely opposite sides like this. This is called anti-paraplanar. Guess what? The alkyl halide could only react in one of these arrangements. Yeah, the E2 mechanism is picky, right? It'll only let us do it in certain cases. You can only have E2 when your alkyl halide is in the anti-paraplanar arrangement. This one, no go. Reason being, you typically have strong bases that have strong negative charges. When the base has to come in over here from the same side as your leaving group, you have a partial negative and a very strong negative getting close to each other, you get repulsion. So that's why you have to have anti-paraplanar. All right? Makes sense? Let's see in practicality how that affects things that you get stereochemically. All right? And what's funny is, remember what I mentioned before about, if you get Z, you can get E. If you get cis, you get trans, etc. That's not actually always the case. You don't always get both of them. Sometimes you do, sometimes you don't. It depends. And you can really only tell which ones you get if you happen to know the 3D arrangement ahead of time, if you have the dashes and wedges drawn. So like in the examples I did before, I didn't have dashes or wedges, I just had flat bonds. If you just have flat bonds, you don't really know for sure. So you need to account for all possibilities. With these, it's going to be a little bit more specific. Let me show you. All right, let me show you this example. Let's say I have this. So what I'm showing you is an alkyl halide. C6H5 is a benzene ring, by the way. Easy way to make it a little bit shorthand. All right, so let's say we have this. Now, if you look at this, the H and the Br are in great positions for E2. They're anti-paraplanar to each other. All right. So, whenever you do this reaction, you form this double bond. You can have a reaction in this particular arrangement. Now, when this happens, the carbons in your double bond, they go to an sp2 hybridization. That means they're flat as a sheet of paper. They're trigonal planar. You don't have dashes and wedges anymore, but you can still have groups on the same side of the double bond. All right. Basically, what's going to happen here is that, there's going to be 2 flat bonds coming out of each of these carbons. If we look over here, all right, at this frozen moment in time, where we have anti-paraplanar arrangements, we see that this group, this C6H5, and this methyl group, they're on the same side, right? They're both on dashes. So that means they're both on the same side of this double bond. This C6H5 and this hydrogen, they're both on wedges, so they are also on the same side. Okay? And if you look at these, the high priority groups are this one and this one. All right? They're on opposite sides of a tri-substituted alkene. This is going to be in E arrangement. And in this example, you would only get E and no Z. All right? Okay? This would be a case where we would not be able to get any different products. Keep that in mind. Take a screenshot of this or do whatever. Have it handy. I can't erase. Come on. There we go. All right. I'm going to show you another example here, and I'm going to tweak it just a touch, but it's going to change things quite a bit. What I'm going to do is I am going to change that methyl group that was on the previous carbon, on the left-hand carbon, into another H. That is going to change the dynamics a bit of this. And what I'm going to do is actually I'm going to tag these two hydrogens with little symbols so you can sort of track them. I'm going to put an asterisk on one. Oh, God. What a ugly, ugly circle. Let me try that again. There we go. Okay? All right, so you see, again, we have, a beta hydrogen and the halogen in a nice anti-paraplanar arrangement. So we can kind of follow what we did last time. Right? We have a C6H5 on the right carbon and an H on the left carbon on the same side. So we would have this. All right? And we kind of have the opposite arrangement with the other groups. And this would be a product, right? This is a di-substituted alkene. And as we can see, this should be, hopefully you can recognize that this is a trans product. All right? And that is one of our products. It's not the only one, though. Don't forget, we're getting constant rotation around this carbon-carbon single bond. And what can happen is these groups can rotate into a position where this hydrogen is actually the one that's anti-paraplanar to your Br. In fact, I'm going to redraw this. I'm going to draw this in a rotated state where I've rotated around that single bond. Okay, so I've rotated the asterisk H around, so it is now in the front. I've rotated the C6H5 to the back, and I've rotated the H with a circle on it over here. So now it is an anti-paraplanar beta hydrogen. And now we can actually get reaction in this state as well. We couldn't do this in the last example because we only had one beta hydrogen, right? So if you rotated it out of the anti-paraplanar arrangement, there was nothing else there. But here, now we see both of the C6H5s are on dashes, and both of the remaining hydrogens, whoops, no, are on wedges. So you actually also end up with this product, and this is the cis. This is why you can get more than one stereoisomer, EZ, cis-trans, in a lot of these reactions. Now, you don't really know what's happening stereochemically unless you have the three-dimensional arrangements. So if I give you a flat one, the one that's all flat, sort of like I did with the other examples, what you need to do is you need to account for all possible stereoisomers. If I gave you one like this, though, you would be able to specify just exactly which one or ones would be present. All right? Okay, I think that is a pretty good stopping point, so I'm going to stop right there, and I will pick up next time. We're not done quite yet with stereochemistry. Next time, we're going to get into chair conformations again, everybody's favorite. All right, well, until then, review this, and if you have any questions, let me know. See you later. Bye-bye.